Okay, so I'm going to explain how to do the second part of this lab. Now, what we're going to do is we have a charge rod. This is an insulator. Like for example, you can get the glass rod that we used in the previous lab. Assume this rod is uniformly charged. That means throughout the rod you have charges, positive charges, and they are uniformly distributed. So if you get a unit length of this charge of this rod, the amount of charge in that unit length is constant throughout the rod. So if you get a section from here, assume this is 1 centimeter, and another section from here which is also 1 centimeter, the amount of charge on this segment A and this segment B, they are this. Assume the total number of charge on this rod is Q coulombs. Okay, so compared to the length of the rod, assume the diameter of the rod is very small. So this is basically a very thin rod. So the amount of charge per unit length equals Q divided by L. This is, I'm going to use lambda to represent the charge per unit length. Charge per unit length, lambda equals Q divided by L. And what are the units of the charge per unit length? Lambda, unit of charge is coulomb, unit of length is meters. So the units of lambda equals coulombs per meter. Those are the units. Okay, now how much amount of charge you have in 1 meter of this rod? So amount of charge per unit length is lambda. That means if you get 1 meter, you have lambda coulomb charge on that segment. So if you want to go with some numbers, assume the Q here. Q is 100 nanocoulombs and length is 5 meters. Then lambda equals Q divided by L. Q is 100 nanocoulombs divided by 5 meters. That's going to be 20 nanocoulombs per meter. That is the amount of charge you have in a 1 meter of this rod. Now what we're going to do here, we're going to find the electric field at this point. This is the origin of the coordinate system. This is the origin of the coordinate system. And we're going to find the electric field due to this rod at that point. Let's see how we can do this. Assume you don't have this rod. Instead, what you have is just one charge particle, like this. Assume instead of this rod, you have only single charge particle, a proton. The charge of that proton is simple Q. You know, you need to find the electric field due to that proton at this point, the origin of the coordinate system. Now, how do we do this? How do you find the electric field due to this positive charge? Now, you know, for a positive charge, electric field is always moving or directing away from the charge particle, radially outward. So the electric field due to this charge particle, this positive charge particle at origin, should be in this direction. That is easy. We can easily get the direction. What about the magnitude of that? So if we know this separation between these 2 points, let's take that as x, which is this distance is along the x-axis. Then the electric field at this point E So I'm going to mark it here. E equals 1 over 4 pi epsilon naught, which is nothing but the electric constant K. Electric constant equals 1 over 4 pi epsilon naught times Q. Q is the charge of that charge particle divided by x squared. And what is the direction? Direction is negative x direction. So this is I is the unit vector along the x direction. So if I put a minus sign here, now we have the direction and the magnitude of this electric field. What about if you have another charge particle, which is here? And charge of that charge particle is also Q. How do you find the electric field due to that charge particle? So I'm going to call it E1 and this is E2. Now we already have the electric field E1 due to charge particle 1. And this is X1 and this separation is X2. This is going to be X1 then. The electric field E2 due to the second charge particle, which is X2 distance away from the origin, equals 1 over 4 pi epsilon naught Q2 divided by X2 squared. And direction is again along the negative x direction. Now we know if you have single charge particles, how to get the resultant electric field. What you have to do is we have to add these two vectors together because they are along the same direction. Now if we come back to our original problem, what we have is large number of charged particles which are close to each other and they are distributed uniformly throughout this rod. Now how do we find the electric field? So the trick is we're going to consider small segment or small element of this charge rod, and this is the element that I'm going to consider, and the length of that element is ds. The length of that element is let's take that as dx. Length is dx. And the amount of charge on that charge, small element, amount of charge on that small element, let's call it dq. Now how do you find the dq? We know the amount of charge on the unit length of this rod, that is called the charge per unit length, that is lambda. So if you multiply this lambda by dx, you will get the total amount of charge on that small element dx. And let's take the separation between this segment, this element, and the observation point is x. Then we can find the electric field dq. Electric field dq. Let me erase this first. Electric field dq at this point, dq, this is the direction of the electric field, electric field dE at this point due to this small charge element dq. And we can write dE equals k, electric constant, the amount of charge on that segment dq, divided by separation x squared. Actually it's simple x, lowercase x squared. And what is dq? We have dq, which is lambda dx. So dE is k lambda dx divided by x squared. Now this is the contribution from one segment. So we have to divide this rod into small segment which equal length, and length of one segment is dx. So this is my next segment, this is the next segment, and this is the next segment, so that I'm going to divide the whole length of this rod into small segment and find the electric field due to each segment and add all them together, because all of them are along the negative x direction, to get the resultant electric field. So if I write the electric field due to this segment is dE1, this segment is dE2, and this segment is dE3. So I can add all these segments together. If you add all the segments together, then you will get the resultant electric field E. Now, since the length of each segment is the same, the amount of charge on each segment is the same. So there's a much easier way to do this calculation, and that is called the integration. Now let me show you how to use integration, or how to integrate this to get the resultant electric field. Now again, so I'm going to consider one segment which is x away from the origin of the coordinate system, or that is our observation point, and the length of this segment is dx, and the amount of charge on that segment is dq, which is lambda times dx, and the separation between the observation point and the left end of the rod is d, and length of the rod is L, and the electric field due to the small segment dx on the observation point, let's call it O, is dE, which is k dq divided by x squared, which is equals to k lambda dx, because dq equals lambda dx divided by x squared. And we have to consider all the segment from left end to right end, so from in this end to this end. So I have one segment here, and I have segments everywhere on the road, and I have the last segment from this side. Now when you go from one segment to next segment, what is changing? So if you go to this equation, the k is constant, so that is constant, that is common for all these segments. If you go to lambda, lambda is the unit charge, charge per unit length, and that is constant, that is same for all these terms. And the next term is dx. What is dx? Dx is the length of each segment, and that is also common for all these segments. But x is the distance to the segment from the observation point. This is the nearest segment, and length is L, length is d, and this is the furthest segment, and length from the distance from the observation point is d plus L. So this x is changing. X is our variable. It is changing from d to d plus L. Instead of adding all these segments together, we can do something called integration. This is what we're going to do in the integration. So we're going to get common terms, or the different letters or the variables in this equation, and see which are common for all these terms and take them out. So E equals k is common, lambda is common. What is not common is x squared, and that is called the variable. And what are the limits of variable? Limits of this variable, it's changing or starting from the shortest length d from the observation point to the furthest point d plus L. And I'm pretty sure you have seen this dx over squared, and this symbol is called integration, integral sign. I'm pretty sure from your previous math classes you learn how to do this. So after this point, it's your mathematical background. So try to do this, try to evaluate this integral and get the resultant electric field. So if you need some help how to do this, then I will explain that in the next video.